Like a phoenix rising from the ashes, astronomers have found a whole new solar system may be forming in the wake of a star's violent death.
This is the hidden universe of the Spitzer Space Telescope, exploring the mysteries of infrared astronomy with your host, Dr. Robert Hurt.
When a massive star reaches the end of the line, it does not go gentle into that good night. It becomes a supernova, an explosion so bright that it briefly outshines everything else in the galaxy. Most of the heavy elements that make up planets, and even people, are forged in the nuclear furnaces of such explosions. Here we see heavy elements in the Cassiopeia A supernova remnant blowing back into the galaxy and mingling with interstellar gases. The next generation of baby stars forms from this material, now enriched with building blocks for growing new solar systems and planets. But what of the star that went supernova? Its core still remains in the form of a pulsar. The stellar corpse is tiny and dense, squeezing about 1.5 times the mass of the Sun into an object a mere 10 miles across. A team led by Dr. Deepto Chakrabarty at the Massachusetts Institute of Technology has found that even a dead pulsar might play host to a whole new generation of planet formation. They studied a once massive star that went supernova about 100,000 years ago. In the process, it likely wiped out any existing planets. While most of the star stuff blew off into space, a little bit fell back under the pull of gravity. Dr. Chakrabarty explains.
If the original massive star was spinning fast enough, then that material won't fall directly back onto the neutron star, but may instead form a disk. And so what we think we found is a disk of this debris material that's left over from the explosion that formed a neutron star.
This disk has about 10 times the Earth's mass and looks very much like ones that produce planets around young stars. Moreover, it may help solve a recent planet-making mystery. In 1992, astronomers found the first planets outside our solar system, which were orbiting an older pulsar. But where did they come from? Could they have formed after their star went supernova? The discovery of a planet-forming disk around a younger pulsar makes this likely. It seems new planets can arise from the ashes of their own star's death. However, pulsar planets are pretty hostile real estate for life. Pulsars provide little light or heat and would bathe these worlds in intense radiation. A nuclear waste dump at the South Pole might actually be a little more pleasant.
The Hidden Universe is produced by the Spitzer Science Center at the California Institute of Technology in Pasadena. The Spitzer Space Telescope mission is managed by NASA's Jet Propulsion Laboratory.
It's been called an exploding galaxy, and 3 of NASA's great observatories have teamed up to show it like it's never been seen before.
This is the hidden universe of the Spitzer Space Telescope, exploring the mysteries of infrared astronomy with your host, Dr. Robert Hurt.
Sigmund Freud once protested that sometimes a cigar is just a cigar. However, astronomers studying the so-called Cigar Galaxy have discovered there's much more going on than meets the eye. That's why they've looked beyond just visible light to understand this galactic oddity. The Cigar Galaxy, more commonly known as M82, lies in the northern skies in the constellation of Ursa Major. It's about 12 million light-years away. Not exactly a next-door neighbor, but pretty close as galaxies go. And while it does look a bit like a cigar, it's actually shaped like a disc. We're just seeing it edge on. Our exploration starts with the Hubble Space Telescope. It celebrated its 16th anniversary by releasing a dramatic new image of M82. This picture reveals in extraordinary detail what we can see in visible light. Dark dust lanes block our view of the star-filled disk, and unusual filaments of hot hydrogen gas extend far above and below the disk. But what's causing this gassy fireworks display? The Chandra X-ray Observatory, working at the high-energy end of the spectrum, helps answer this question. These X-rays originate from million-degree gas in M82, heated by violent star-forming activity known as a starburst. Here, in a tiny region in the galaxy's core, stars are forming 10 times faster than within our entire Milky Way galaxy combined. Giant stars are exploding as supernova every 20 years or so. These blasts drive out the hot gas in geyser-like flows moving at millions of miles an hour. At the other end of the light spectrum, the infrared eye of the Spitzer Space Telescope adds a surprising new discovery. At shorter infrared wavelengths, the starlight from M82 shines clearly through the dust. We can see all the way into the central starburst. The real surprise is the huge dust halo seen at longer wavelengths. It's over 20,000 light-years across, and it's the brightest ever seen around a galaxy. This dust is made of organic compounds, similar to those found in car exhaust or on a barbecue grill. The cigar is indeed smoking, and its smoke reveals the same elements that make up planets and even people may be escaping into intergalactic space along with the gas. So what causes a nice galaxy to blow its top? It may be due to a dust-up with its neighbor. Not far from M82 is its companion galaxy, M81. It's pretty normal as galaxies go, with regular spiral arms. Spitzer's infrared view shows its red-tinted dust lies in orderly lanes along the spiral arms, not in a chaotic halo like M82. Astronomers think that 500 million years ago, these two galaxies had a close encounter. The gravitational tides were much harsher on M82, disrupting it and creating its starburst. When we combine the X-ray, visible, and infrared views from Chandra, Hubble, and Spitzer, we see this tortured galaxy in a way the human eye never could. Starlight glows in yellow-green, the hot gas is blue, and the smoky dust is red. This great observatory composite of M82 reveals at a glance this complex starburst galaxy and the materials it's recycling back into the universe.
The Hidden Universe is produced by the Spitzer Science Center at the California Institute of Technology in Pasadena. The Spitzer Space Telescope mission is managed by NASA's Jet Propulsion Laboratory.
This new Spitzer image has unsheathed the sword of Orion and led astronomers to a treasure trove of baby stars within.
This is the Hidden Universe of the Spitzer Space Telescope, exploring the mysteries of infrared astronomy with your host, Dr. Robert Hurt.
Orion the Hunter is one of the best-known constellations in the sky. Hanging beneath its distinctive 3 belt stars is a glowing patch known as the Sword of Orion, or M42. At a distance of about 1,300 light-years, this nearby stellar nursery is easily visible to the naked eye. But for astronomers studying the Sword of Orion, visible light alone just doesn't cut it. We see only the small patches where young stars heat the surrounding gas and make it glow. The bulk of the Orion Cloud Complex is a mostly dark swath of dust and gas, containing the mass of about 100,000 suns and spanning 250 light-years. The infrared eye of the Spitzer Space Telescope can see this dust directly and identify the vast population of infant stars buried within. Spitzer can find young stars by detecting the infrared glow from their surrounding dusty disks. The very youngest stars are gobbling up material from their disks and growing larger. Later, the leftover disks around adolescent stars can provide the resources for building planets. Our tour of the Orion Nebula starts with the brilliant cluster of 1,000 stars residing in a bowl-shaped cavity in the larger cloud. 4 of these stars, known as the trapezium, are massive giants. Their dust-destroying ultraviolet light alone was enough to hollow out most of this cavity. The most prominent infrared feature here is the next generation of massive stars, which are completely hidden in visible light behind a fold of dust. Their expanding shockwaves heat the gas around them, producing a brilliant green glow. Most of the stars in this ultraviolet-drenched region have dust disks, and astronomers are studying how this affects the potential for planet formation. Dr. Tom McGath, the lead investigator of this project, explains.
These environments, these hot environments around massive stars like there's in the Orion Nebula, where there's a lot of UV radiation, may have a dramatic effect on the disks. It may actually sort of erode and basically evaporate the disks. While in contrast, the disks that are far away from it and more isolated in small groups or in isolated regions wouldn't have to deal with those kind of processes.
Looking to the north of the Orion Nebula, we find a colorful region laced with dark veins of dust. The stars here appear to be forming in an orderly progression, with older stars on the left and younger ones on the right. Many of the green blobs here literally point to nearby star formation. As infant stars feed on their surrounding disks, they eject fast-moving jets of material. When these jets slam through distant parts of the surrounding cloud, they produce shockwaves that glow green in Spitzer's vision. Even to the south, where there are no massive stars lighting up the dust, modest-sized stars are clearly forming in abundance.
These are features that you can see throughout the region, and one thing that you can actually do with this data is trace back the jets to find where the stars are. And you can look at the morphology of the jets and their shapes, and you can try to figure out which star is generating which jet.
Dr. McGath and his team have used this data to make the most complete census to date of star formation in Orion. They have identified about 200 growing baby stars and over 2,000 young stars with planet-bearing disks. That's a lot more than we knew before, but the demographics of this census are even more important. If we think of the main Orion Nebula as a large metropolis of star formation, then about 60% of the stars were born in the big city, with 15% coming from smaller towns or clusters. This leaves a surprising 25% that grew up in isolation, far more than expected. Astronomers are working to understand more about the differences between these stellar city slickers and country bumpkins. This may someday help us figure out where and how our own solar system was born.
The Hidden Universe is produced by the Spitzer Science Center at the California Institute of Technology in Pasadena. The Spitzer Space Telescope mission is managed by NASA's Jet Propulsion Laboratory.
It's as clear as day and night, but on an exotic alien world, astronomers have for the first time measured the temperatures varying across the surface of a planet beyond our solar system.
This is the Hidden Universe of the Spitzer Space Telescope, exploring the mysteries of infrared astronomy with your host, Dr. Robert Hurt.
Planets orbiting other sun-like stars are notoriously difficult to observe. They're so distant that no telescope is yet powerful enough to photograph them directly. Their feeble light is blurred into the glare of the stars they orbit. Nonetheless, since 1995, astronomers have discovered over 200 extrasolar planets by observing the effects they have on their parent stars. These include gravitationally induced wobbles and even faint dimmings of the starlight when the planets pass in front. The infrared eye of the Spitzer Space Telescope has already proven to be an exciting tool for learning more about these alien worlds. In 2005, astronomers Drake Deming and Dave Charbonneau announced the first detection of light from 2 extrasolar planets, seen as they went into eclipse behind their stars. Now, astronomers Joe Harrington of the University of Central Florida and Brad Hansen of UCLA have taken this one step further. They have actually measured differences between the day and night sides of such a world.
So this particular system, the star is called Upsilon Andromeda because it's in the constellation Andromeda, and this actually has 3 known planets orbiting it, named conventionally just B, C, and D. And this particular one we're looking for is a signal from Epsilon Andromeda B. So that's the closest planet. So this is a planet that's actually orbiting its parent star in about a 4.5-day orbital period. So it's much closer to its parent star than, say, any other planets in our solar system are.
This planet isn't just an extra hot Mercury. It's a gas giant as massive as Jupiter, and while there's nothing like it in our own solar system, astronomers have found it's far from unique. Many so-called hot Jupiters have been discovered around other stars, but very little is yet known about what these roasting balls of gas are really like.
And so the natural question that came about was, how does this increased amount of energy that they're receiving from the sun affect the structure of the planet and its atmosphere? So some models suggest that in fact the light is absorbed and re-radiated very quickly, so that the heat is coming out mostly on the day side rather than the night side, whereas other models suggest that maybe if there are very strong winds, such as give rise to the bands on Jupiter, then in fact the light can be distributed, the energy can be distributed quite evenly around the planet before it gets re-emitted.
To test these models, Harrington and Hansen needed to observe this system in the infrared, where the planet emits most of its light. Though the star is over 100 times brighter, Spitzer could still pick out the small variations in the combined brightness as the planet moved through its orbit.
So we went out, we tried to observe the system to see whether there was a day-night temperature difference, and we found in fact evidence that there is a strong day-night temperature difference between the day side and the night side, based on the fact that we see this characteristic variation in the total light from the system over the course of 4.5 days, and exactly in the right phase, in the right time to correspond to this model, where in fact the day side is hot and the night side is cold.
The temperature difference is immense, over 2,500 degrees Fahrenheit or 1,400 degrees Celsius between the comfortably cool night side and the broiling hot spot facing the star. This is vastly different from the infrared structure of Jupiter, which is even temperatured all around. This remarkable result marks the first time any kind of variation has been seen across the surface of a planet outside our solar system. For now, only imaginative artists can provide pictures of what they could look like. But until the day we can take real snapshots, astronomers will continue to find clever ways to explore this growing catalog of alien worlds.
The Hidden Universe is produced by the Spitzer Science Center at the California Institute of Technology in Pasadena. The Spitzer Space Telescope mission is managed by NASA's Jet Propulsion Laboratory.
Ask an astronomer. What is a redshift?
Astronomers often use the term redshift to describe how far away a distant object is. To understand what a cosmic redshift is, think about sound. Sound travels in a wave. You hear the engine of an airplane because the waves travel through the air to your ear. If the airplane is moving, the sound waves in front of it are compressed, creating a higher frequency sound. The sound waves behind it stretch out, creating a lower frequency sound. As the airplane passes you, you will hear the familiar Doppler shift. Light also travels in waves, and a similar thing happens to these waves. Light waves are able to compress and stretch, thereby changing their frequency or color. Blue light has shorter wavelengths than red light. When an object in space moves towards us, its light waves are compressed into higher frequencies or shorter wavelengths, and hence we say that the light is blue shifted. When an object moves away from us, its light waves are stretched into lower frequencies or longer wavelengths, and we say that the light is red shifted. So, how does redshift define distance? Well, the light from most galaxies in the universe is redshifted, as seen from the Earth, because the universe is expanding. It turns out that the farther away a galaxy is, the faster it's moving, and the faster a galaxy moves, the more its light is redshifted. So measuring the amount of redshift is a good measure of the distance of the galaxy. Using this cosmic redshift, astronomers have measured the distance of galaxies as far away as 12 billion light years, and we're always pushing that cosmic limit farther back. For Ask an Astronomer, I'm Dr. Tom Jarrett at NASA's Infrared Processing and Analysis Center.
Ask an astronomer. How can we see a black hole?
A black hole is one of the strangest objects in outer space. For one thing, a black hole is not really a hole, and it's not empty. It's actually filled with a lot of material crammed into an extremely small space. Scientists think that black holes are created in places where the force of gravity crushes an enormous amount of matter together, making it incredibly dense. This can happen in the centers of large galaxies or when a giant star collapses and shrinks during the final gasp of its short yet brilliant life. Like the tug of gravity on Earth, a black hole exerts the same kind of force on its surroundings. But with these fantastically compact and massive objects, the gravitational pull is so strong that even light can't escape. That is why the object is black. It does not give off any light. It's as if you were looking at a black hole. So we can't see black holes directly. However, we can see the effect that they have on the region of space around them. Since black holes have extremely high gravity, the surrounding material, like gas and dust, is funneled into a disk around the black hole. The gas atoms in the disk swirl around the black hole so fast that they heat up and emit X-rays and even higher energy light. By finding this very hot material which is spiraling into black holes, astronomers can locate them and study their properties. So astronomers study the motions of objects in space to see where there is material that might be moving, as if a black hole were affecting it. The motions of stars would be most unusual if a black hole were nearby. So far, evidence has been found for the existence of black holes in the centers of several large galaxies and in binary star systems. That's where two stars orbit each other. And yes, there's even a very large black hole at the center of our galaxy, the Milky Way. But don't worry, the black hole in the center of our galaxy is much too far away to be any danger to Earth. For Ask an Astronomer, I'm Dr. Tom Jarrett at NASA's Infrared Processing and Analysis Center.